So thank you very much for that. Okay, on to the topic at hand. So, small smart telescopes mean small integrated cameras and telescope systems. And we have two of them right here to show you. This is called a C-Star 50. It's a 50 millimeter aperture telescope system. Computers are built into all of these things, and this costs about $500. The system in back is called a Dwarf 2. It's a 2-inch aperture. Or 1-inch aperture, sorry. And it's being replaced with a larger aperture version. Same thing on steroids, basically. And this is about the same price as the C-Star. The other main present competitors are made by Unistellar. And while they have a little bit more capability, they cost a lot more. They go from a $500 price point to a $2,500 price point. And the Unistellar, the largest one is 4.25-inch aperture. Now look at none of them have cooled cameras. Okay, so you actually will get your absolute best imaging in the middle of winter. But they work okay, for pretty much everything in summer as well, if we had clear skies. So none of these are really suitable for planetary imaging. Yes, you can see maybe a couple belts on Jupiter. You can convince yourself you have a ring on Saturn, but the focal lengths are just too short, and the pixels are just too large, and the aperture is just too small to do justice to any of the planets. But frankly, rank beginners can turn out pretty acceptable images of deep sky objects. They are not bad little scopes, and they offer a lot of capabilities in doing interacting with other people. Some of them allow you to have 8 or 10 handsets hooked up to them at one time, with one person driving it and the other people just downloading images. It's pretty cool. Okay, so how do we do science in astronomy? Largely, it's through using modern CCD and CMOS imagers to make measurements and take images and make measurements from them. What do I mean by measurements? We do position measurements, it's called astrometry. We do brightness measurements, photometry, and in order to get the composition of objects, spectrometry. And these telescopes are capable of doing pretty much all of that. So why do I want to do science imaging with these small smart telescopes? So you've laid out $500, and you've taken about 30 or 40 pictures of the Orion Nebula. And that's like, now what? You're looking for some follow-on after taking a bunch of pretty pictures, generally. Unistellar met that need with their popular telescopes by actually hiring I believe it's 5 staff astronomers on a part-time basis. And those staff astronomers push out projects to Unistellar owners. People are asked to take pictures of a particular comet, a particular asteroid, or whatnot, and send the images back to Unistellar. The staff astronomers do studies, do papers, and publish, and any of their users who send images in are listed as co-authors, which is kind of cool. But not all the telescope manufacturers do that, and there's a big. I'm concerned personally. I think there's a big cost of doing that. In most cases, when you buy a C-Star 50, it costs ZWO so much money to make it, and then they sold it to you, and they're making so much profit. And that's the end of the story for them. There was a cost, there was a return, they're done with you. In the case of Unistellar, they have these astronomers are paying, so they're not done with you. Every year, they're increasing their costs to support you. And I, as a former businessman, I don't know how long that will be a sustainable model. Okay, if their sales flatten out, that could be difficult to justify. And that's one of the cool things about them, though. So we'll see how it goes. This is from Unistellar's website, and about the kind of projects they offer. I think this is a pretty sexy website. They have their asteroid program, planetary defense, so it's near-Earth asteroid observations, exoplanets, comet, and cosmic cataclysm program. Cosmic cataclysmic program is variable star measurements for the most part. And astronomer Bert Pablo, who presented earlier, actually sends Unistellar suggestions on a monthly basis of what to observe. So there's a good relationship there. So just earlier today, Mark mentioned he was saying 8-inch telescope's a good size minimum for exoplanets, and I would tend to agree with him. But I've seen some of the light curves from a 4.25-inch Unistellar that were not bad. They were pretty noisy, but you could see that when it decreased in magnitude and when it increased. But that's as far as I'd say I'd go. I've seen light curves of exoplanets from the ZWO C-star, and the user who took those images swore that he could see a decrease in brightness. I kind of tipped my head in various directions, and I just couldn't squint enough to make me see that. So I would say 2 inches is probably below the limit. So I've had experience with both the C-star and Dwarf 2. And these other scopes may be used to do science as well. So let me go through with what we can do and some of the limitations. So exoplanet transits, I don't think anything as small as a C-star can do that. Maybe a Unistellar, but that's only on a very large, hot Jupiter that has a relatively large decrease in magnitude, in brightness. Most of them can't do it. It's just fundamentally the others, they're all too small. They're all too noisy because the cameras aren't cooled, so there's a lot of thermal noise there. I can almost convince myself, I can't convince myself that I can see a decrease in brightness in that light curve, but man, look at the noise there. I don't think you can get much meaningful data out of that. Asteroid observations. This is interesting. So I don't know how many of you are familiar with the Harvard College Observatory's Minor Planet Center, but the Minor Planet Center is like the repository of asteroid position and magnitude data. When a new asteroid is discovered, observers go out and make a lot of observations, send them to the Minor Planet Center. They publish the orbital elements of it and follow it for a long period of time. They also collect data on rotation rate of asteroids. But in order for them to collect your data, they have to basically bless you first. They have a program for you to get your Minor Planet Center observer's code, and that requires you to go out and do, I believe it's 6 asteroids fainter than 14th magnitude, and follow them over the course of several days and report their positions. And one of them has to be a fast mover or near Earth orbit kind of asteroid. And if you have residual errors compared to other people's data of less than 2 arc seconds, they'll give you your Minor Planet Center code. I know at least one person who's gotten a Minor Planet Center code with a C-star, and his residuals were half an arc second, so were 4 times better than required. So I'd say that these small telescopes can be used for that. So I mentioned you do rotation period measurements. Again, these telescopes are like set them, point them, and forget, and they just keep taking images. So you can just set them up once during the night and let it keep taking images of an asteroid and then analyze it in the morning. There's software called Tycho Tracker that's inexpensive and it's used a lot in this kind of analysis. Comets. The Minor Planet Center also tracks comets and does orbital elements for comets. Again, these small telescopes are very capable of providing you with good data for that. Variable star photometry. So variable stars are everywhere, and I'll show you what I mean by that in a minute. But like, you take an image of the Orion Nebula, and you will accidentally image well over 100 variable stars. In fact, less than 10% of the stars in the Orion Nebula star field are fixed and not variable. There's a bunch of types of variable stars. There are binaries. I think Mark talked about binaries earlier, two stars revolving around each other. There are cataclysmic or exploding stars, nova, supernova, stars that physically pulsate in size and brightness. And then there's some stars that are surrounded by rotating gas and dust clouds and clumpy matter makes them brighter or makes them fainter periodically. So this is my present favorite. It's called it has a poetic name of V1117 Hercules. And this is, where's the point? Is there a pointer here? Well, anyhow, this shows data for the last 5.5 years or so. The star used to have very regular periodic dimming of around 3 magnitudes every 400 plus and minus days. It wasn't fixed 400. It was a little bit of variability on that, but it was like once every 400 days. And then all of a sudden, back in 2021. It went nuts, and now it's totally random, and some of the periods from faintest to faintest are as short as 7 days, and no one knows why. I'm into it just because anytime I get the data, I add it to this curve, and just to see what's happening next, because you never know. So this is the Orion Nebula star field. And all of those indicators are indicators of variable stars. You'll note there's a very few that don't have those indicators in that field. Okay. So a little bit about AA, VSO, and variable stars. We provide lots of support via courses, classes on how to use our software tools, classes on how to analyze data, classes on just the different types of variable stars. Manuals are all free from our website. You don't have to be a member to use them. Forums where we give advice or answer questions, and again, you don't have to be a member to use those. We have databases going back 111 years plus. I didn't realize we had data from the 1500s of variable star measurements. We also have a database on exoplanet transits. We maintain that database for NASA. And recently, 2 years ago, 3 years ago, Bert, I think we started a database of stellar spectra for people who are 4 years ago, for people who are spectrometrists. Say that 3 times quick. And we provide analysis tools and mentoring, and we're just fun people. So, one of the things is, I think I might have mentioned earlier, is we tend to use the green channel from these color cameras and not use the blue and red channels, and I want to show you why. So, the problem with blue and even green on these sensors is, so the green, you see the green curve, it drops off at around 650 nanometers. But notice that in the infrared, it goes up so that at about just beyond 800 nanometers, it's almost as sensitive in the red, or in the IR, as it is in the green. And the blue is more sensitive in the IR than it is in the blue. So we tend not to use the blue, and red just is high until way out in the infrared. The other thing we like to do is put in infrared cutoff filters. Both the Dwarf 2 and the C-Star have infrared blocking filters to help get around that problem. So that's a good thing. Unistellar does not have an infrared blocking filter, but if you have smaller hands than mine, you can get a standard 1.25 inch infrared blocking filter, reach behind the sensor, through the not crosshairs, the sensor holder, it's the spider, and get in there and screw on a minus IR and just leave it in place. Don't even think about running it, varying it. The other reason we tend to use just the green channel is, so there's several curves on each of these charts. The black curve is the sensitivity of the sensor. So the green curve shows it's real sensitive in the green, and it's also real sensitive to the infrared. There's a red line, which is basically a square wave filter to just cut off everything but that color, green, blue, or red. And then there's the color filled in area, and that's basically what a standard filter is. That were back in the 1950s, standard color filters were designed and began to be sold for photometry, and those are the transmission curves of that. The green filter, so the green filled-in area, pretty closely resembles the green sensor, except out in the infrared. So they're close. The red is very different. The blue is very different. And the reason that's an issue is because in many cases we're trying to match data, or we're adding to data sets that were begun 50 years ago or 100 years ago. And if your filters are significantly different, then your data is significantly different than that. And really, it's questionable about whether they should be in that database. Does that make sense to folks, or is that a little too obscure? I know Mario's confused, but. So the workflow for any photometry is straightforward. Review what we call our DSLR manual, but it really covers any color camera. Download it, review it. You image as usual and get FITS file images, and all of these telescopes will generate FITS files, just a standard file. Extract the green channel, there's free software to do that. Calibrate the green channel image. Mark, I think, was talking about BDF, calibration, bias darks and flats. So you do that. You analyze the calibrated FITS images using whatever package you wish. Maxim DL will do it, Astro Image J, VPhoto for AVSO members on our website will do it, Tycho Tracker will do it. In spectroscopy of brighter stars is also very possible. The easy way to do that is to buy what's called an SA100 grating and put it in front of your small smart telescope. You could screw it basically right in front of the Dwarf 2, and you have to make it a little adapter to put it in front of the C-star, and away you go. That produces spectra of all the bright stars in your field of view. They don't have super high spectral resolution, but you'll be able to, come up with, the classifications for all the stars in the field, A, B, O's, whatever. AVSO maintains a database of stellar spectra, so you can send your results in to us. And we have a spectroscopy observer's manual. So what's done with all this? We have these databases. Who cares? Well, the variable star database is it's over 110 years old. It's available for download for researchers, students, you, me, whoever. Last year, AVSO data was used in over 200 publications. That's compared to, I believe, Hubble. I think last year, we actually did a search on this. Hubble data was used on 90 papers. So that's kind of cool. Spectra collected is available to researchers. The Harvard Minor Planet Center collects, analyzes, and distributes their data to observers. And the other kind of cool thing, if you contribute to the AVSO databases, is the professionals go pretty regularly in and extract data and use them in papers, in studies. I've been fortunate enough, and I've only been observing these for 5 years, but I've been fortunate enough to be contacted by a researcher in Belgium, of all places, thanking me for observing a star he's interested in and saying, oh, if you're observing this star, would you observe this star and this star as well? So I started getting data from those stars, and they're very appreciative of it. In another case, just last year, one of the stars I was, by happenstance, observing, because it was of interest to me, a professor out in Washington State reached out and said, I'm writing a paper on this star, and I'm going to use your data. Can I list you as a co-author? It's like, yeah, throw me into that briar patch, you know? It's encouraging to know that people are actually looking at and using your data. And on a weekly basis, AAVSO reports out to its observers if anyone accessed their data that they contributed. They don't tell you who asked for it, but they'll tell you if it was a student, a researcher, or other, I think, are their categories. So you know when people are looking at your data. So I know my talk was a little short, sorry, but I didn't have a lot to say. Anyone have any questions out there before you charge my tent and go after all the tchotchkes? This year, I apologize. Last year when I was here, I had pens. I threw them out to everybody who asked a question. Somebody reminded me that I could have put an eye out, and I didn't bring pens. So, and when you ask questions, speak up. I'm not young like Bert and Mark and Mitchell. Thanks.
So the software that you listed there that helps you do photometry with telescopes, I'm not familiar with sort of the principle of operation there. Is it just when the telescope saves an image, it's saving data basically?
Yes.
Is it just looking at that data, or is it analyzing the images?
So he's asking me, what does the image analysis software do? It varies a little by package. Being an AAVSO member, I tend to use our own software most, and I find it very friendly. It's called VPhote. And what happens is through the web application, I bring up an image of mine, and then from a drop-down list, I say find all the variable stars in the field, and it identifies them. And then I click on find the comparison stars in the field, because there are known fixed brightness stars all over the sky in our database. So it brings up those, and I say, okay, I want this variable, and this variable, and compare them against this comp star and that comp star. And it does the analysis for me.
So what's it doing? Integrating the brightness of pixels across the image of the star?
Yes. One of the things I have to set up is like what size circle am I measuring in? There's a measurement diameter circle, then there's an exclusion circle, and then there's another circle that's background sky noise, with no stars in it. And it just automatically takes all that into account. And I try to, in a perfect world, I'd have signal to noise ratios of well over 100 in the analysis. For sometimes, for that star I showed earlier, V1117 Hercules, it's typically around 12th magnitude. Okay, great. And I'm getting signal to noise ratios of 200. But then it dropped to 16th magnitude in 3 days. I'm kind of screwed. The signal to noise ratio goes down to 25. It's like, I'll take it. It's what I got. Well, actually, that data is not being taken from these. I'm kind of a lazy astronomer. I've got an observatory in my backyard, some good telescopes. I have a borrowed sea star. But what I do is, one of the other things that AVSO has is that Bert mentioned, is a network of telescopes in the US, Australia, I think we had one you used to have one in New Zealand. I don't know if it's there anymore. Still there? Okay. And yeah, you would know, wouldn't you? And one of the people who maintains our networks here, and does a great job too. But anyhow, I could put a proposal in that I'm interested in this star, and a couple people on the committee look at the proposal, and proposal takes 10 minutes to put together. A couple days later, I'll either get yes, we'll observe it for you and send you images, or no, we won't, usually because they're already giving those images to somebody else for the same star. And then anytime it's clear and that star's in the sky, I get I get B, V, and R, and I images of it sent to my account, and I just go do the analysis. So I only do play stuff with the home telescopes. Yes?
I'd just point out that the new Stellafane Raza, you mentioned it briefly, but the only negative is it's pricey, about $4,000.
Well,
It has none of the negatives that you mentioned.
well, it actually, well, not quite. Mario mentioned the new Stellafane Raza automated scope doesn't have any of the negatives I had mentioned, and actually, I think it does. Well, first off, it's going to be pricey. It's about $4,000, I believe. Second, I know they'll get it right eventually, but it's really not a product. It's still in beta test, and they're still screwing around with the software 6 months after they announced it. So maybe it'll be a product soon. But I believe their camera is not cooled. It is cooled. Okay, that is good. And it'll be able. Okay, it'll be able to go fainter just because it's a 6-inch instrument. I think it's f2 or 2.5. Yeah, so that'll be interesting, but at a big outlay of cash. So, yes.
What's the procedure that, say, the C-Star does, if you want to get darks and flats, and will it calibrate images?
It does darks by itself. It's transparent to you. None of these small telescopes I'm familiar with do flats, but I believe the reason they don't do flats, and I've taken a really close look at stretched images from them all, the sensor is so small compared to the field of view that you're just picking up the center of the field of view, and it's pretty flat. I just don't think it's an issue. But they all do darks.
So if you were doing vertical star photometry, you would take the dark corrected images and get about those flat?
Yeah, I would. And as of now, this is going to change in the future, hopefully near future, but George Silvas here from AAVSO has done a heck of a job writing software for our VPhoto application that when I upload like a C-star image into VPhoto, it recognizes from a C-star, it recognizes it's a 3-color image, and it outputs a bunch of different files. It outputs a green file, a file of just the green pixels, the red pixels, the blue pixels, and actually I think it does three green files now. The two individual channels and then the combined green channels. So that is not a sustainable thing for us. Frankly, we do all of our analysis and storage out in the cloud, and these images, especially if there's a lot of users, they're big and expensive to handle out there. We have a separate group working, hopefully in the short run, to come up with a different way to analyze, where we come up with what's called star lists. Like in your computer, we give you software or provide software that doesn't just send up the images, it sends up the essentially right ascension, declination, and brightness in all 3 colors of each star in the field. And that data gets set up. So instead of being like 15 meg to 25 meg per image, it's Mark Mulcasey, if he's here, he told me the number. Mark, what is it, like how big are your files?
I seem to remember 200 to 1 shrink.
200 to 1 shrink. So it's much more economical. So hopefully that'll be available in 6 months, maybe a year, 6 months to a year. Yes?
How does the quality of the seeing affect your data?
Well, yeah, that's a good question. As long as so seeing affects data, right? The spots get bigger. As long as you integrate all that light from that spot, you can get good data. If you have a small circle that you're taking data from and your image is a lot bigger, then you're kind of cherry picking and you're missing a lot of data. And that's a problem. But all you have to do is look at your image and see how big the image circle is. As long as it covers a star, you're golden. But obviously, good seeing helps everybody, right? Yeah.
You get a lot better signal-to-noise ratio if you keep focusing.
You could, and in fact, these small smart telescopes allow you to defocus. There's like an autofocus feature, which I use, and then if I'm doing variable star work, I'll autofocus, and then I'll go to manual focus, and I'll go out of focus a couple clicks. Yeah, just go out of scope. Anyone else? Mario, you're going to harass me. You haven't yet.
I'm thinking of an embarrassing question. I'm just
See, he can't even find anything embarrassing to ask me. What a guy. Okay, well, again, thank you all for giving me the opportunity to speak and, to organize this Pro-Am collaboration thing. We'll hope to see you again next year. Oh, and if anybody wants to take a look at the dwarf or sea star, I got them both here.